In this video, we're going to talk about the least squares regression line, which is a best fit line for a set of points which minimizes residuals. This is our overview slide, which we'll spend about 5 minutes going over before we then spend our time looking at each topic in more detail and with more examples. The least squared line is a best fit line for a set of points, and in general, in choosing a line for linear regression, we will define a best fit as one that minimizes residuals. So even with this definition, we can have many different formulas, and so the ones we will be using is the least squares criterion or the least squares line, and that's the one that minimizes the sum of the square of the errors. The least squares line is useful when, one, we have linearity. The data shows a linear trend. If there's a nonlinear trend, we need a different, more advanced regression method. The other criteria we have is our residuals need to be nearly normal. We also need constant variability. The variability of points around the least squares line must remain roughly constant. Finally, we need to be cautious about applying regression to time series data, which are sequential observations in time, such as stock data. Such data may have an underlying structure that should be considered in a model and analysis and not simply jump to a least squares line. The formula we will be using is the point slope form of the least squares line, and that formula is y minus y naught is equal to the slope times x minus x naught, where x naught is the sample mean of x, y naught is the sample mean of y, and the slope is the standard deviation of y divided by standard deviation of x times r, where r is the correlation coefficient. The slope describes the estimated difference in the y variable if the explanatory variable x for a case happened to be 1 unit larger. The intercept describes the average outcome of y if x equals 0 and the linear model is valid all the way to x equals 0, which may not be the case. Another point, extrapolation is treacherous. Linear models can be used to approximate the relationship between variables. However, these models have real limitations. The truth is always more complex than our simple lines. For example, we do not know how the data outside our limited window will behave. So in other words, if we have sample data for a certain range of x values, then our linear model might not be valid outside the x values that our sample data has. Using r squared to describe the strength of a fit. So we have our r here as part of our slope. So r squared of a linear model describes the amount of variation in the response that is explained by the least squared lines. Finally, we look at categorical data. So categorical predictors with 2 levels, categorical variables, we must convert to categorical data into numerical form, are also useful in predicting outcomes. The estimated intercept is the value of the response variable for the first category, i.e. the category corresponding to an indicator value of 0, and the estimated slope is the average change in the response variable between the two categories. So this will become more clear with an example. That concludes our overview, so now we can go back up and take a closer look at the least squares line. The least squares line is a best fit line for a set of points. In choosing a line in linear regression, we define a best fit as one that minimizes residuals. There are many formulas that we can use to minimize residuals. The one we will use is called the least squares criterion or the least squares line, and what it does is it minimizes the sum of the square of the errors. There are certain conditions that make the least squares line useful. First, we must have some linearity, so the data must show a linear trend. If there's a nonlinear trend, we need a different, more advanced form of linear regression. Second, the residuals must follow a nearly normal distribution. Third, there must be constant variability. In other words, the variability of points around the least squared lines must remain roughly constant. And last, we want to be careful that we have independent observations, and in particular we want to be cautious about applying regression to a time series data. In other words, data that unfolds over some period of time, which are sequential observations in time, such as stock data. Such data may have an underlying structure that should be considered in a model and analysis, and not simply thrown into a least squares line. I left some of the notes on least squares line up here for your reference, and I also shortened it a little bit to give us some space for our first example. Our first example is the graph below considers family income and gift aid from a random sample of 50 students in the freshman class of Elmhurst College in Illinois. Gift aid is financial aid that does not need to be paid back as opposed to a loan. The scatter plot below is shown along with two linear fits, these two lines. One is dotted and one is solid. The line follows a negative trend in the data, that is, as the values of X get larger, family income gets larger. In general, you can see that the value of Y, the gift aid, goes down. We can pick 2 points to kind of see that or illustrate that. Somewhere over here, where family income is 50K, we can see the gift aid is somewhere in this range, these 2 points. Whereas over here, when we have family income around 200K, you can see the gift aid tends to be lower. These yellow points are lower in gift aid than for the lower income family. It may not be true for every single point, but that's the general trend. Our first question is the correlation positive or negative? So if it's positive, as X increases, Y also increases. They increase together when it's positive. If it's negative, that means when one increases, the other decreases. As we mentioned, in general here, as family income increases, the gift aid decreases. For that reason, we will say there's a negative correlation. As X increases, Y decreases. Our next question, should we have concerns about applying the least squares regression to the Elmhurst data? And what we're asking is if these criteria here fit the data. Our first criteria is linearity. And as we mentioned, it does seem like these points roughly cluster around a line. It's not like fully some scatter plot where there's a little cloud of points. It roughly follows a line. So we'll claim there is some linearity. The next criteria is residues must be nearly normal. So to do this one, we would have to plot the residuals, which I haven't done yet. And our last criteria is constant variability. Well, actually, there's one more after that. Constant variability, well, yeah, there's sort of constant variability. The difference between these points and the line, they're roughly, this distance away, whatever this, or within some distance away. It's not like they're wildly scattered far away from the line, and then some of them are super close. They're pretty tight around the line. There is one other criteria. I didn't put it here. Independent observations. This is not time series data. So this point doesn't come in time before this data, and this point comes before this data. In other words, this x-axis here is not about time. This is about, at the same time, we take a bunch of students and we sample them. So this is not time series, so we don't have to worry about this fourth criteria or fourth issue. These 4 graphs illustrate 4 examples where different parts of the least squared line conditions are not met, and so we should not be using the least squared lines. This first one violates linearity. In other words, there is a trend of association, but it tends to be more of a parabolic shape, right? The one that's kind of shaded. It's not a line, but a parabola. This one here, well, this looks pretty linear. There's this one kind of outlier. Here we have the residuals that are plotted. So you can see that we have, it would be nearly normal, except this one outlier. So in this case, this one outlier might throw off our line. If maybe this outlier is like something really unusual in data and you want to throw it out, that's something you consider. If you consider throwing this point out, you have a nice linear line. If this point is considered important, well, then you may not have as linear a trend as you think because you have this important point outside the line. This third one here where we say we must have constant variability, the variability around the least squares line remains roughly constant. You can see here there's not a lot of variability, but as you increase x, the variability gets larger. So here you do not have constant variability. You can also see this in the residuals. They get larger over time. And this last example is time series data. And you'll know time series data because usually the x-axis is time, or someone will tell you that we're looking over time. Our next topic will be the point slope formula for the least squares line. Our formula now for the line is going to be y minus y naught equals slope times x minus x naught, where x naught is the sample mean of x and y naught is the sample mean of y, and the slope will be the standard deviation of y divided by the standard deviation of x times r, and r is the correlation coefficient. We'll bring back our last example. That's the family income versus gift aid for our 50 students from the freshman class in Elmhurst College. Let's see, here's our scatter plot, and we have additional information that the median family income is $101,780. So here on family income, we have the mean over, let's see, somewhere around here is our mean x value. The family income standard deviation, so for x, is 63,200. Then our mean gift aid is 19,940. So where's our mean gift aid? It's somewhere very close to 10,000. And the gift aid standard deviation is 5,460. And finally, the correlation, which we talked about in our last video, it talks about how closely our points are to this line, how closely they cluster around the line. Correlation of +1 is a perfectly straight line going upwards. Correlation of -1 is a perfectly straight line going downwards. And as we go towards 0, the lines become less and less tight around the line. So here we have kind of in the middle correlation, a downward, that's this negative trend. And it's not super tight around the line, but it's not super random either. It's right in between. So I summarized our problem here. I put our chart here so we have more space. Next, I'm going to summarize this data here, but I'm going to put it in terms of our symbols that we have in our least squares line. So first, I'm just going to identify my variables x and y. So x is family income and y is gift aid. And now I want my x naught and y naught, which is my mean x and my mean y. So my average x naught, I should have put x naught instead of x. X bar is my average sample x, which is equal to, it's given to me here, 101,780. Then my average y, my y bar, my average sample y, where's y? Mean gift aid is 19,940. And I'm just going to add the x naught here and the y naught here so I can just plug it into this formula, which is what I do here. My least squares line then is y minus y naught, which is my 19,940, is equal to my slope. And my slope is standard deviation y over standard deviation x. So I guess I need to look that up. Standard deviation y is 5,460 divided by standard deviation x, 63,200. And then I need to multiply that by r. So r was given to me as negative 0.499. And then finally, after the slope, I need x minus x naught. So x minus an x naught is my 101,780. So this is the formula for my line right here. Actually, this is the formula. And if I'd like, I can do some algebraic manipulation. I multiplied these three, I did the division and then multiplied to get negative 0.0431. And then I multiplied the slope by x and slope by my 100,000 over here. And I also moved my 19,940 over by adding to both sides of the equation. So now I have the slope y-intercept form of the line, of the equation for the line. Either of these equations will work. We often see this form because we think of plugging in x and then solving for y. But you can certainly plug in for x here, do all the calculations, and then add the 19,000 at the end. So this formula will work just fine as well. And something I want to mention, this line here is the solid line in this picture. So the solid line in this graph is the least squares line. We have a question. Suppose a high school senior is considering Elmhurst College. Can she simply use the linear equation that we have estimated to calculate her financial aid from the university? And the answer is yes, but it is an estimate based on last year's data, and for any given income level, there is variability. Again, so this is last year's data. Who knows what financial aid is going to be this year? And then the last point is, let's say her family income is 100,000, so we're in this kind of range over here, or somewhere in here. For this value, the estimate is going to look like this point on the line in yellow. But you can see that there are these different, different people got different levels of income support, even though they had a very similar income. So she can estimate it, but there is variability around the line. There are a few more things we should talk about with this point slope form of the line. So the slope describes the estimated difference in the y variable if the explanatory variable x for a case happened to be 1 unit larger. In other words, what happens when we change x by 1 unit? What happens to y? The intercept describes the average outcome of y if x equals 0, and the linear model is valid all the way to x equals 0, which in many applications is not true. So let's bring back our example to explore these two questions. So what do the slope and intercept for the Elmhurst data mean? We had calculated our slope as standard deviation of y over standard deviation of x times r, which is negative 0.0431. So we plugged in our slope into our equation y equals slope times x plus our y-intercept. So here is our slope, negative 0.43. And what that tells us, for every dollar increase in income, again, as we change x 1 unit larger, so every dollar increase in income, we expect this 4 cents, it's $0.0431 less gift aid. And here we say we expect less gift aid because the slope is negative. If the slope had been positive, we would expect this amount more gift aid for every $1 increase. That means for a $1,000 increase in income, we multiply this by 1,000, we expect $43.10 less gift aid. Let's now look at this y-intercept. Remember we talked about, where did we talk? The intercept describes the average outcome of y if x equals 0. In other words, here when we plug in x equals 0, this goes away and we have y equals $24,316. So what this means, if a student has no income, x equals 0, the gift aid we expect is $24,316.54. But this may be extending the data too far. An even clearer picture or example of when we extended the data too far, let's calculate the aid for a family with income of $1 million. So we're going to plug in our $1 million here for x, and we get y is equal to negative $18,783.46. And there really isn't a negative gift aid, because the negative gift aid would imply that the student would owe more money, this much more money in addition to tuition, but that isn't really how aid works. So there's no negative aid. And the reason why we're extending this, why we say this is extending, is our data only covers up to family income, maybe up to 300,000, not even 300, but somewhere here, maybe 270K. So we're going into dangerous territory by the time we try to extend our data, our x values, much further than this 250K. The next idea we want to take a closer look at, using r squared to describe the strength of a fit. The r squared of a linear model describes the amount of variation in the response that is explained by the least squared lines. So let's bring back our example. And let's calculate our variance in aid, which is the standard deviation squared. So our aid here is 5,460 standard deviation. We square that, and we get 29,811,600. And this is the variance in y of our sample data, which actually seems way too big, right? Because, the difference between our lowest income and our highest income, it looks like it's 30K. So in fact, the least squares model provides a better way of estimating y based on x that reduces variance. What we use instead is r squared, which is our negative 0.499 squared, which is 0.25. So variance is reduced by 0.25, 25% by using family income to predict gift aid using a linear model. Our last topic will be categorical predictors with 2 levels. So we're going to look at categorical data. That's data that isn't numerical, but we have to convert this categorical data into numerical form if we want to make a line. But we can use this. It's useful for predicting outcomes. Actually, I think it's kind of suspicious, but anyway, we're going to do it anyway. The estimated intercept is the value of the response variable for the first category, i.e. the category corresponding to an indicator value of 0, and the estimated slope is the average change in the response variable between the 2 categories. This is where an example is really helpful to illustrate. So consider eBay auctions for a video game Mario Kart. We have both the total price of the auction and the condition of the game, used and new, recorded. So the price is a nice numerical value. The condition, though, is a categorical variable. It's not a number, used and new, but we can code this as a number. So here we want to predict the total price based on game condition, and a plot is shown below. So we're going to code used as a 0 and totally new as a 1. And in between you can have something almost new, so 0.7 or something is the idea. As you kind of rate your newness, you convert your categorical data into numerical. You can see here if something is only used, like if we only have the condition used and new, nothing in between. When it's used, this is where our price points tend to be. We have something that sold as low as $30, something that sold as high as something around $65. If we have something that's brand new, then the lowest price tends to be somewhere around 40 or a little over 40, whereas the high price tends to get towards 80. And again, just to summarize, the price is numerical, that's great. Condition is categorical. We can go from used all the way to new, so we're going to convert totally used as 0, totally new as 1. So here are some of the statistics based on these points here. So we don't have all these individual points, so I can't recreate these statistics for you, but we basically just have this plot. But the 2 ones that we're interested in is here, the condition used and the condition new. So what this condition used, the intercept is, that's where x equals 0. So on our scale of condition from 0 to 1, where 0 is used and 1 is new, if used is equal to 0, then what we see is the median price. Here we're looking at this data here, right? Where it's totally used. The median price ends up being $42.87. So that's this one here. The condition new, that's over here on our graph when we have a brand new thing. We're looking at these prices here, right, in this column. We can see on average the price is a little over 52. And it is actually exactly $10.90 more than the $42.87. And because it's $10.90 more, that is our slope, right? For every increase in our category data from used to new, we expect another $10.90. So that's where this formula comes from here. Again, this 42.78, that's our average price for our completely used, condition equals 0. This is our average price for used. And then here, our average price for totally new is $10.90 more than the $42. In other words, it's the $52 over here. So here's our price. So when condition is used, we expect $42.87. And when condition is 1 is new, we expect $10.90 more. As I mentioned, I consider this kind of sketchy, but it is kind of clever. And if you need an estimate, this is a good way to do the estimate. I can't think of a better way. Okay, to review what we've covered in this video, we talked about the least squares regression line, which is a best fit line for a set of points. And it's best fit in that it minimizes residuals. But even with this minimized residuals criteria, there are many different formulas that will satisfy this. And what we use is the least squares criteria or least squares line that minimizes the sum of the square of the errors. So the least squared line is useful when we have linearity. The data shows a linear trend. If there's a nonlinear trend, we need a different, more advanced regression model. It's useful when the residuals follow a nearly normal distribution. Also when there's constant variability, so the variability of points around the least squared lines remains roughly constant. And last, there's this warning for independent observations. We want to be cautious about applying regression to time series data which are sequential in time, such as stock data, because such data may have an underlying structure that really should be considered and not just thrown into a simple least squares line model. Next, we talked about the formula for the point slope form of the least squares line. We used y equals y naught equals slope times x minus x naught, where x naught is the sample mean of x and y naught is the sample mean of y. The slope was equal to the standard deviation of y divided by standard deviation of x times r, where r is the correlation coefficient. We talked about how slope describes the estimated difference in the y variable if the x variable is increased by 1 unit. We said the intercept describes the average outcome of y if x equals 0, and the linear model is valid all the way to x equals 0, which in many cases is not true. We warned against extrapolation. So linear models can be used to approximate the relationships between variables. However, these models have real limitations. The truth is always much more complex than our simple lines. For example, we do not know how data outside our limited window will behave. So if our data is collected for x values between 0 and 10, plugging in an x value of x equals 50 may or may not be anywhere near what it should be because we're extending our window too far. We also talked about using r-squared to describe the strength of the fit. The r-squared of a linear model describes the amount of variation in the response that is explained by the least squares line. And finally, we looked at categorical predictors with 2 levels. So we have categorical data that's not numeric. We had to convert the categorical data somehow to numerical form. And then we could predict some outcomes, and we had an example of that. So that's it for this video. Thank you for watching.